Okay, so welcome back. Let's look at what the products are for this bromohydrin formation here. Here's the solution. Here are the two products you form. First, see, you have to add the water to the more substituted carbon, right? That's the regioselectivity. So that means the OH ends up on the carbon of the double bond on the left side, which has the methyl and the ethyl group attached, right? So it ends up on the tertiary carbon, the OH. Now, there's again two enantiomers which form in this case, and so they are drawn here. Again, they result. There's different mechanisms actually how they can. No, they result like this. So basically, you have the double bond, the Br, the first enantiomer results from having the Br2 attack from the back side of the double bond. So you make a bromonium ion where the bromine is pointing toward the back, and then you open that up with water, which is coming from the front. Okay, that leads to the first product. Now the second product forms by having the bromine attack from the front of the double bond, so that you form a bromonium where the bromine points to the front, and then the water opens it up from the back side. Okay, so that's how you get those two enantiomers. So try to draw out that mechanism, and practice some more. Very important. Now next, I'll show you again a very similar reaction, and this reaction is called epoxidation. It's a very useful thing. It's a way basically where you can add two OH groups in the end to a double bond. Okay, and the epoxide is an intermediate. So it's a three-membered ring with oxygen now instead of a three-membered ring with a bromine in there. Okay. And so first some definitions. Essentially what we're going to do, we're going to convert an alkene, right, like before, to a three-membered ring, which now instead of a bromine contains an oxygen. And such a ring is called an epoxide. So you need to know this term. That's an epoxide. A three-membered ring, two carbons, one oxygen. And here's how it works. This is the mechanism of how epoxides form. It's literally just one step, but this mechanism has it in it. So you need to make sure you can draw these arrows. Okay, having every final exam I've been asking this kind of arrow pushing. I might do this again. So here's how it goes. We have a double bond. Now to form an epoxide, we have a really special reagent, which looks kind of like a carboxylic acid, but it has an extra oxygen inserted, right? And so you see what this does is it has a leaving group. Basically, it's just an acid group, right, which is attached to an OH group. You see, you recognize the leaving group there, right? So that's kind of like carboxylate anion, so COO minus. Okay, like for example acetate or things like that. Of course, resonance stabilized. So it's a good, the green stuff there, the green things highlighted, or it's just good leaving groups. Now, I can take that away to get some space, and essentially what happens is now, because we have a leaving group attached to that terminal OH group, we can attack that OH on the top there with again the double bond is the nucleophile, like always. And so then we push away the leaving group. And we're going to do a cyclic arrow pushing, because now you see we are pushing the electrons into the carbonyl oxygen, the CO double bond, and that makes that oxygen of the carbon-oxygen double bond makes a single bond to that oxygen, makes it O minus, and then that acts as a base now to take off the hydrogen, which is attached to the initial OH. Okay, and at the same time that frees up electrons of the H, which we take H plus we take away, which now these electrons can attack the double bond as a nucleophile. See, that forms all in one step. And a concerted mechanism, it forms a three-membered ring with the oxygen. Okay, and that's called an epoxidation reaction. It's an epoxide, and the side product is just an acid, carboxylic acid. Okay, that you need to practice this arrow pushing mechanism. I hope it helped you guys to see where it's coming from by recognizing this carboxylic acid moiety as a good leaving group. That helps, I think. And yes, so this special type of reagent, right, you've just abbreviated it as R, it's called a peroxy acid. Okay, peroxy just usually means that you have an oxygen-oxygen double bond in the molecule. And so what it is, it's just, it's a carboxylic acid with an extra oxygen inserted. Okay, so that's used as a reagent. Now here are some actually two common reagents which are used in practice. The first one is just this is essentially acidic acid, which has an extra oxygen inserted there, right? And so that's called peroxyacetic acid. Okay, now the other one is much more complicated. It has an aromatic ring with a chlorine, and the chlorine is in a so-called meta position. You will learn this, what meta, para, and ortho means later, okay, in the spring semester. But this compound is called, the name is metachlorobenzoic acid, and so it's abbreviated as MCPBA. So what you need to know is pretty much this. You don't actually, it's good if you know the structure of MCPBA. You don't absolutely have to. What you need to know, you have to recognize the structure as a peroxy acid which does epoxidation reactions. Okay? And you have to recognize the name, and you have to recognize MCPBA as something which does epoxidation reactions. That's the important part. So now in the presence, important thing to note is that actually these epoxides, they are stable compounds. And it's very different from the three-membered rings, right? The charged cationic three-membered rings with bromine, the bromonium ions. Those are not stable. Those you cannot isolate. These rings with the oxygen, you can isolate them as long as you don't have strong acid or very strong nucleophiles like RS minus present. So you can isolate these things as intermediates. It can be very helpful for synthesis. But then what you can do is you can go ahead and you can open up these epoxides. And generally you do this with acid. Okay, so these epoxides, they are just ethers, right? They're ether functional groups. And ethers, like water, you can just protonate these compounds because you have an oxygen. So if you have a strong acid, you can protonate the three-membered ring oxygen, the epoxide oxygen, and that generates a really good leaving group. Right? We have done this before with water, if you have with alcohols. So if you have an alcohol, then it's not a good leaving group, but then if you protonate it, it becomes a great leaving group. You've seen that, and then you can do an SN2 reaction there. So essentially we can do the exact same thing with epoxides. And so the protonated epoxides, then they will be opened up. Yeah, they will be opened up, again in an anti-fashion with backside attack to form a diol, a so-called diol, because you get two OH groups. That's what happens with water. So let me show you how this happens. Okay, this is now our epoxide starting material. And first, we just protonate it. So for example, we take H3O+, right, and that will protonate our epoxide. Here is the protonated form. You see now that the oxygen has been converted into a good leaving group. And now you can take the water, and the water will act as a nucleophile. It will attack from the back side of the epoxide in a SN2 type reaction, and you basically have this OH leaving group. So that what happens is, so on the left, the OH leaving group is pointing up. On the right, it's pointing down, because that came from the water. Okay, but of course you don't form this directly. First, what you also form an enantiomeric structure of this, but this is protonated, right? Because the water again came in and attacked a cation. Finally, in the last step, you have to deprotonate again the the oxonium ion like we always do. And so you deprotonate like this, and then you get your final diol products. Okay, why is it called a diol? Because an alcohol is called an ol. So if you have two alcohols, then it's called a diol. Okay, and then you form the enantiomer. If you open up the epoxide in another way, if you instead of it with the water attacking the right carbon, you attack with the water, you attack the left carbon, follow through the same mechanism. That's how you get the enantiomeric product in this case. All right. So you might start to feel that we are actually discussing a lot of different reactions, and I have a fear that you're starting to feel a little confused. And so I want to give you one slide which really puts everything together a little bit better, okay? So what we are actually discussing here is always literally the exact same, almost exact same mechanism, okay? And we have seen pretty different species, but I want to show you the similarities of these species by listing them all together. Okay, it has been all about three key intermediates, which are three-membered ring intermediates, right? These three-membered rings, they always contain two carbon atoms and then one other atom. And look what this other atom is, right? We just had a protonated epoxide, which acts as an intermediate, right, which can be opened. That's one of these three-membered ring intermediates. It's just opened up from the backside, right? So that's one of these. Another thing we have seen, right, is a bromonium or chloronium ions, and again, it looks very similar. Just the oxygen or the OH plus is replaced by a Br plus. Okay, and again, it gets opened up with nucleophiles from the backside. At the same time, we had also seen the mercurinium ions, right? And there, again, they look very similar. Three-membered rings. Now here just the bromine or the OH plus, they are replaced by mercury plus. Okay, and again, it could be, we saw this, it can be opened from the backside of a nucleophile. So what makes these three-membered ring intermediates, great intermediates, to be opened up is a ring strain, right? Because a three-membered ring is highly strained. It wants to be opened up. When you open it up like a spring, it releases its strain. And then the formal charge, the positive charge, makes this thing highly electrophilic. And so any nucleophile, even a weak nucleophile like water or an alcohol, will want to open it up from the backside. Okay? So that is what is happening. And yeah, the key thing is too, right, that you always open all of these intermediates up from the backside, and so you always form anti-products, right, where the nucleophile is coming in from the backside, and then, for example, the bromine is on the other side, okay, or the OH is on the other side, or the mercury is on the other side. Very important. Don't forget about this. So the opposite side of the leaving group, nucleophile ends up on the opposite side of the leaving group. And you need to practice this stuff. Okay, so this is with conceptual, or with skill builder 8.7. Alright. I would like to end up with some more practice. Okay, so I'm going to give you, again, a reaction. I'd like you to predict all the products of the following reaction. Here we go. An olefin, and it reacts with FCPBA. Then this is followed by reaction in sulfuric acid and in methanol this time. So the question is, what product forms? What are the products which form? And you need to think about, again, regioselectivity, if it's important, stereoselectivity, stereospecificity, all of these things. Anti-addition versus syn addition, right? Things like that. So I'd like to give you a couple minutes, try to figure this out. If the lecture is already ended, just think about it for the next lecture on Wednesday, and then we're going to go over the solutions. Thank you.